Hello, everybody. I'm Cartwright-Cox. You may know me as the sort of bgp.tools guy. I don't actually only do bgp.tools. I also occasionally do the systems engineering bit. So, LONAP was looking for better monitoring on the Internet Exchange. And this is not a novel problem. Most Internet exchanges have some form of fabric monitoring, mostly to enforce like service level agreements, basically. And as far as I could understand while looking around, most of these were just turnkey appliance boxes. You can just buy a box, place them in all your things, and it'll tell you if there are problems in your backbone. And so it's not actually that hard of a problem. And ideally, you would expose all your metrics to vendors. Some IXs do, some IXs don't. It's quite useful for a member to figure out, am I broken, or is the Internet Exchange fabric broken? And depending on how clueful the IX member is, when they know this knowledge, they may or may not even bother to raise a support ticket, or at least certainly not during the incident, which is not particularly welcome. I don't know. I'm sure many people here have operated a network and done something slightly wrong and achieved the inbox 0 to inbox 900 in the span of 5 minutes. So sometimes if you can answer that question for them ahead of time, that's very useful. Standard monitoring. You send an ICMP ping, thing comes back, you see how long it takes, you see if it did actually arrive. If stuff is broken on latency or stuff is broken on loss, then you do an alert. The problem is, this quite seriously hides the complexity of modern day fabrics, especially Internet Exchange fabrics. So in reality, at least LONAP, looks like this. So you have effectively a bunch of these links. Each one of these switches, these customer POPs, have multiple ways of getting to different bits of LONAP. This is done through something mostly called link hashing. So basically the parts of the packet, mostly the source address, the destination address, the source port, the destination port, and potentially a few other things, are taken from the packet, pushed into a magic black box, which then determines which path you're going to use. In reality, of course, there are significantly more than 2 links per POP. There's a whole bunch of them because you need this for capacity. So some POPs may have like 8 different ways, maybe even more, to get to a spine, which then gets you onwards to your destination. Also, of course, sometimes one of these is going to be faster. Also, even between the spines, some of them are going to be more loaded. So some of them are going to be faster. The optics may themselves be faulty. And so maybe one is just lossy. Maybe if you're just really unlucky and you get the Sod's Law hash, you're going to lose packets. A normal ICMP solution will not pick this up, or it may pick this up, but it will be astonishingly rare if it does. So my solution for them is I wrote something called IXP ping. The software to do this kind of already exists. So Automatic of WordPress fame, and I think they bought Tumblr, wrote this thing called Pingo. It's extremely good at detecting what I just described. Unfortunately, it requires policy-based routing to be set up, which is not particularly ideal for this use case. And there is also TWAMP as well. It feels a bit complicated. The networking vendors really threw their weight behind it. I'm not a massive fan of it. It feels a bit like using a grenade launcher against squirrels. It's technically valid, but doesn't really solve the problem. Or it does solve the problem, but Anyway, so ideally, what you really want is some software that you can just throw a single machine, bunch of interfaces in, and can handle multiple switches, monitor things. Because a lot of the time, Internet Exchange will have multiple switches in the same POP to handle different customers. So you're not mixing your 1 gig customers with your 400 gig customers, because a whole bunch of slightly boring technical reasons. You don't want those on the same switch. The final code comes in around 650 lines of code. Didn't say it was very complicated. It could be fancier, but sometimes that has downsides. Complexity is something you should control. So in practice, there is 1 machine per POP that is plugged into all of the switches. These machines are not particularly exciting. They're just some cheap, I think, secondhand HP kit with some RAM, some generally quite boring NICs. Mellanox CX3s and the Intel X520s, very well established, very well sane NICs. And what they effectively do is they create some ports on each one of the NICs and then ping all of the other NICs and see what happens. So ports, yeah. And in the middle, it doesn't know anything about the topology of the network. It's just trying every single one of the NICs to try and get all of the hashing paths involved. So yeah, each monitor machine has more than one NIC. Each NIC is a customer-facing switch. I don't monitor the spines because customers don't see the spines. There's no need to measure them. You measure the impact of the spines going bad, not the actual spines themselves, because customers don't care if the spine goes bad if they can't necessarily feel it. So yeah, each NIC has a bunch of UDP ports that all the boxes overping. Ping is sent every 250 milliseconds, and packet loss is calculated on a sliding window of the last 32 packets for each NIC. I've only shown 2 ports here because I don't want to do that much PowerPoint art, but imagine there's 32 or 16. A note on latency. I mentioned earlier, or I'm not sure I mentioned, but it was in the slide, that I wrote this in Go. So Go has a garbage collector, and so even the best garbage collectors at some point need to do something called stop the world, which basically is what it says on the tin. It stops the entire execution of the program to go and do some stuff. Go has a pretty good, pretty advanced garbage collector, but it still does actually need to, for a few microseconds at least, stop the world every now and then to go and clean up some garbage. This happens in Xping as well, and so there's a few interesting things we can do here. We can have the kernel, the Linux kernel itself, timestamp stuff. So instead of me measuring the time when I get a packet, I can tell the kernel to tell me what time it received a packet. So even if we were busy garbage collecting or being stopped, having the world stopped, we would be fine because we can just use the kernel's timestamp, and the kernel isn't subject to these things. This doesn't work on the transmit path, but jitter in this path is quite rare. It's pretty astonishingly rare to be interrupted halfway through creating a packet and it coming out. It does happen, but it is quite rare. And to solve that, it's quite a lot of extra work. You kind of have to make your packets look a bit like precision time protocol, as far as I understand, and the kernel, the interface for doing this is particularly janky and not necessarily pleasant. And I wanted to keep this as simple, as maintainable as possible. It also means that if you go down this route, there is no chance in hell that you'd ever manage to port this to something like FreeBSD if you, for some reason, wanted to do that. Yeah. Enabling this is really simple. It is literally just 2 syscalls to say, hello, I would like timestamps enabled, and I would like your timestamping to be done in software. You can have it done in hardware, but you'd also then have to make sure that every NIC from there on has the correct driver support for doing it in hardware. Once again, I just want these things to be working all the time. Not worth it. You don't gain that much. You don't save that many microseconds by doing that. Another fun note on Linux ARP behavior. So note that I mentioned that there is one machine with potentially 3 NICs to 3 different customer-facing switches. Linux has some very interesting liberal defaults on how it responds to ARP. So if you have an IP address on your first NIC, and then someone on your second NIC ARPs for NIC 1's IP address, NIC 2 will respond with its own MAC address. This is very fun on a wide internet exchange, because effectively you have some NICs stealing each other's IP addresses all the time. This also is a really good way to lose a lot of time wondering where the magic packet loss is coming, where the magic packet loss is the entire fabric updating where stuff is. So this is particularly fun. There are some sysctls that you can set. I don't know why this is not a default. I'm sure there's some extremely long-haul lore on why Linux is like this. There are not other operating systems are like this, but boy, can this one steal a lot of your time and drive you slightly up the wall. Anyway, exporting out data is pretty standard as well. So about half of the industry status quo now is Prometheus, as far as I can tell, or the modern stack at least is Prometheus. So Xping or Crossping exports its data out as a Prometheus server. So Prometheus server has some boring recording rules to make the website queries a little bit faster, and then that stuff goes into Grafana, which is basically now the industry de facto standard as well. That has public viewing enabled. It's pretty boring, nothing particularly to write home about. The critical concern as well is obviously you want the operators of the exchange to know that they have a problem somewhere, and so that's quite easy as well. Prometheus is itself an alerting engine. It's quite easy to plug it in. Yeah, especially very easy to quickly point out with, basically you can write alerts. It's quite simple to do. It's really basic stuff now. Anyway, here's what you're probably waiting for. Pretty graphs. So is there a laser pointer in this? Is that a laser pointer? Oh, OK, well, look at this. There are 3 separate bands. Isn't that really cool? That's like showing, so that's between Telehouse East and Interaction in Brick Lane. There's 3 distinct different latency paths you can use to get there. Obviously, clients don't know this. They're not deciding this. This is just the fabric magically deciding. For me, it's really cool just seeing this in the graph. It's proof that it works. And yeah, as I mentioned earlier, there is jitter. This is almost certainly around transmission, like getting garbage collected at just the worst time. But because we're talking this would not be visible in almost all use cases, but because we're talking microseconds, hundreds of tens of microseconds being a very visible thing, you do kind of see it sometimes. But for the most cases, I think this is fine. Another fun thing, if you look at all the switches latencies to all of the other switches latencies, you can pretty much see the London to Slough gap. I do really enjoy when server providers claim that Slough is London. Where they're like, I think for a long time ago, like DigitalOcean was like, oh, we're releasing our new London data center location. And you're like, oh, is it Slough? It's Slough. It's not really London. Anyway, you can really actually tell that it's not really London from some of the switches that's like a whole millisecond away, which, I assume back in 2015 didn't feel like a big deal, but there are certain applications now where you would at least notice on graphs the millisecond. So I think that's fascinating. And you can Slough is in fact quite far away. In fact, I think it's outside the M25, which means it is certainly not London. Also, one direction. If you take just the raw speed of light in glass, assuming the most stupid as the crow flies, no one is bulldozing straight through Southall certainly to get to Slough. It's about 100 kilometers of fiber on a round trip, so about 100 milliseconds. So about 1 millisecond sort of makes sense in terms of like how long it takes to get to places. So this is now live. You can look at the LonApp metrics at fabricmetrics.lonap.net. And if you want to run this yourself, the software is open source for other people to use. And the instructions are provided, so you can easily build and run it. The code will be going up shortly. Thank you for listening to me. And if there's any questions on how this stuff works or any other questions about Internet Exchange monitoring, I would love to talk to you about it.
Hello, it's me again.
Hello.
I forgot to say earlier, I work for Glide, but nobody cares. Did you find yourself having to do interesting maths on what the noise floor is? Because I figure when you're doing such fine measurements, what is significant change and what is not gets interesting.
Yeah, to some degree, if you start... Because switches are in use with... Slightly hearsay moment I might be about to say, but so in my eyes there are two different major routers. The major differences now between a router and a switch is basically its buffer size, right? Like you pick up your average Arista and you can absolutely perform as a router. The only serious difference in my eyes is that one has a great big honking buffer and one doesn't. So because this network is mostly switches, because it's an internet exchange, there's basically no buffer, so the latency stuff doesn't really matter as much. You would see loss before you would really see serious latency. If you're running some big routers, there are some internet exchanges that run rather large routers in place of switches, you might see higher latency spikes because it's holding onto the packet for longer if there's like congestion. In this case, that's probably not going to happen, and so you could set alerts on latency. I would probably set alerts if you could see more than 2 milliseconds. Because shouldn't need to be able to that shouldn't be possible on the speed of light in optimal conditions, or at least shouldn't be. It will be possible, but it won't be optimal. So that's worth alerting on. But as far as like general noise, it's not worth really thinking about. You would see loss way before you would see serious latency.
Cool. And my other question is: have you considered talking to the guys who are here from ZPE? Because they might be interested in you writing the feature for their nifty monitoring boxes.
Well, they can just use the open source code if they really want to. Or you could hire me, that would be great too. But
Hi Ben, David from Arista. Thank you, I think this is really cool and fascinating. Sorry if I missed it. How do you ensure that, let's say where you have a large number of interswitch links, like maybe your traffic is being hashed over, say, 8 links, how do you ensure that you populate all of those links? Do you just fire lots of different flows
fire
and hope
lots.
they all get hashed?
Because of course you have no real control of. Let's go back. Let's go back very far. There we go. It's a black box for a reason. I don't know many. I don't know cases where people have. Other than the Linux one, but that's software routing, and you don't particularly want to go and you're not optimizing for that. It's really hard to calculate what the vendors are doing. Sometimes I don't think the vendors know themselves because it's a Broadcom blob of doom. So the answer is you just have to fire as much as you can, right? So if you take a rough guess of like how many unique paths, double it, hope that you don't lose the lottery by somehow managing to miss a link. The risk of this is that you might actually do miss a link. The answer is you just have more ports, which has processing implications, but mostly it's fine.
No, good to know. Thank you. Maybe I'll catch you in the break. I think I've got some ideas of if we want to pin traffic to certain links. There are some tools we could maybe look to do that.
Yeah. I wrote a long time ago. So this is sort of already done with ECMP. So I wrote something a while ago that basically just broke ECMP on purpose, where if you wanted to target one specific machine on someone's backend, for honestly good reasons, I promise, then it would basically could quickly calculate what you would need to do to only ever talk to that one machine. So this is possible. It's just on long-haul networks, obviously, that's not great.
Yep. And then one obvious to me follow-up question is, once we have this data, and maybe this is more of a question for OneApp and other exchange operators, is once you have this data, could you then use it to automatically cost out links if they go over a certain threshold of loss or latency and so on?
You mean like sort of like a weird ECMP auto bandwidth, or
no, just cost out the link in BGP, right? Just set a high local pref or something.
Oh, so if the link is faulty or whatever, then you could, you could potentially try and do that automatically. Ideally, it would be quite nice if there was some vendor option to be like, hey, do BFD or something between each point to point, and if the BFD doesn't, I don't care if the BFD goes down, but if we start losing BFD packets, then it would be quite nice to start sunsetting that link. But that's a dream. Maybe it exists. Maybe it exists in TWAMP. I don't know.
I'll catch you later. Thanks, Ben.
Is there one more? I think there's one more.
Yeah, you know me, Brian Candler. My question is just about how do you get that accuracy of your timestamps? Are you just doing regular NTP, or have you got satellite?
So you don't need, because the packets themselves contain the local machine's time. So the way this works is you have the server, the monitoring machine sends its ping, and the other side's job is to literally just reflect it as fast as possible, to bounce it as fast as possible straight back to you. That state is entirely tracked inside the packet, so you don't need any NTP synchronization, which is really critical because you can get some really nasty, like NTP synchronization is really hard, especially in the microseconds. So you have
this
to
is just round trip times you're measuring, not
It's really
one
just
way.
round trip times. If you had PTP, you could do so much other fun stuff. For example, you could do point-to-point latency. In theory, that shouldn't be that interesting, but it can be quite interesting, especially if you have weird hashings or unequal costings. There is no PTP on LANApp, which means that you can't easily do this. Not right now, at least.
Thank you.
Hi, Mike Hughes, contractor and doing some work for one of our sponsors, Star. So effectively, when you're doing this, then based on the last question, actually what you're doing is you're monitoring a pair of paths because they're not symmetrical, right?
There'll be a return path.
There'll be a return path as well. And then the other thing, yes, Slough is definitely not London. I was working at Lynx when we went to Slough, and I remember the soul searching that we had to get outside the M25, and we had to ask the members really, really nicely. That's just a little bit of history for anybody if they're interested. I'm trying to think that, I'm just really glad to see this. I remember Rob Lister and I years ago racking our brains on it, so I'm really glad to see it.
My conspiracy theory is that Slough was set up by the people selling long-haul links. It's so much cheaper, honestly.
I remember how expensive those optics were.
Yeah.
Hi, Tim Chan, JISC. So another really good talk. Thank you very much. It's something where we might look at the code. You mentioned if you had PDP, what do you think the main barriers are? Is it just a lack of interest? Is it vendor issues? What would prevent PTP being deployed and used?
PTP is just PTP at even moderate scale is kind of hard. You have a bunch of the answer is a whole. I think precision time in the industry is an entire sub bit of the industry on its own, and so there's a lot of things that can go wrong with PTP. The equipment around it is kind of mythical. Not many vendors are doing. The answer always is like how precise does your time need to get? And there's just not much other than vendor boxes, turnkey appliances, and things like that. There's not many good systems out there to produce good open source time that you can audit yourself. Like you can say, yes, I understand how that works. And it's, for me at least, it's quite hard to deploy something where I don't really understand how it works. I don't like a magic box where you plug a GPS signal in and it goes, yeah, sure, I promise that I'm sending out the right time. That's not good enough. The only exception to this is that Facebook, or Meta, I don't know which brain does it, which side of the brain, but they are doing really good work on time cards, like effectively just FPGA on a stick that produces reliable PTP because Facebook uses a lot of PTP for their databases or database synchronization. And so they've done a whole bunch of good work. There may be work like this in the future on internet exchanges. I know NetNod does PTP on their LAN as a service. They advertise that quite heavily. So maybe PTP is a service that people want. It's hard to know. But yeah, PTP is certainly not something that you can do easily, because if you do it badly, people are going to hate you. Also, depending on if you're a financial services company, that might be extremely bad because regulations requires you to have your time within a certain set of microseconds from UTC, and if you get that wrong, you're out of compliance, which can be very awkward to explain to a regulator.
Yeah.
So
Okay,
PTP
thanks.
is just one of those really deep subjects that you can just get lost in.
Yeah, I think there was you make that point, there was a really good blog last year from the Facebook or Meta team, the engineering team, a really in-depth dive into how they are deploying PTP and the software they've written for it. It's really good. I don't know if anyone from Facebook or Meta is here, but that was excellent. But yeah, thanks for the answer. Thank you.
No worries. Is that it?